Hi, I'm Leo from Colab Cambodia, and this is the final installment in the first series about how to build a simple electrical circuit. In the previous videos, we've introduced you to components, we've drawn their circuit symbols, we've constructed a circuit diagram, we've used that to build a circuit, and then we finally measured it with a multimeter. Now it's time to go back to the basics again and work out how we really should have done this process. When you're designing electronics, you need to know about the numbers for the circuit you're using. That means knowing about its intended purpose, knowing about the capacity and the size of the battery you're going to use, knowing about the values of the components that you want, and knowing about what you really require from things like LEDs. How much light do we actually want to come from them? So when I measured this circuit in the last video, we found that a few of the values were a bit different to what we were expecting. For starters, we found that this battery was actually using or generating 9.6 volts instead of 9 volts as advertised. When I measured the voltage drop across the LED, I told you expect 3 volts and actually only gave us 2 volts. That's because the color was different from the one I had in my head. And then finally for the resistor, I told you to expect 220 ohms and it actually came out closer to 230 ohms, assuming that our multimeter was accurate. So we can work backwards from these numbers to find out what kind of current was flowing in that circuit and see if it was really appropriate for the LED that we were using. A typical amount of current that you want for an LED is something like 15 to 20 milliamps. 20 milliamps is 1/50th of an amp. It's quite a small amount of current, but that's more than adequate to light an LED. Any more than that and the LED will start to get hot. So let's learn how to work backwards from those numbers to get to the amount of milliamps flowing through the LED, which is our target value. As I told you before, an LED has a certain amount of voltage that it likes to drop in a circuit. In this case, it's 2 volts, and that leaves over a chunk left for the resistor to deal with. The resistor's job is to eat the remaining voltage and turn that power that it's used into heat that comes out of the circuit. If you're really using a resistor to its fullest extent, you can touch it and feel that it's getting warm or even hot to the touch. There are 2 formulae that you need to know in order to work out power use and the relationship between volts, the voltage of a circuit, also called the electrical height, current, measured in amps, that's the amount of electricity flowing, and resistance, that's the value which determines how difficult it is for current to move through a certain component. And here are those 2 formulae. V equals I times R. Voltage equals current times resistance for one component. And the second one is power, P, is equal to the current times the voltage for a certain component. So we're going to use these 2 now to back calculate the current in this LED. This is a very common task and one you should be familiar with. Total voltage of the circuit, V, 9.65 volts. The voltage drop across the LED is 2 volts. So if we do 9.65 minus 2, we get 7.65 volts. And we know now that that is the amount of voltage which must be dropped across the resistor to get back down to 0. So the resistor is using 7.65 volts. We also know the resistance of the resistor, it's 230. So we're going to use this first formula, V equals IR, to work out the current flowing through the circuit. The current in a series circuit is the same at all points. So if we work out the current for the resistor, that means we also have worked out the current for the LED, which was our target. If I rearrange this to V over R equals I, then I can plug in the numbers. I'm going to get 7.65 divided by 230. So we're going to take V equals IR and we're going to rearrange it to make I the subject of the formula, since we have the voltage and we have the resistance for the resistor. Remember that the current is the same at all points in a series circuit. So if we manage to work out the current for the resistor, that's the same as the current flowing through the LED. V over R equals I. So we have 7.65 volts divided by 230 ohms. 7.65 volts divided by 230 ohms gives us 0.033 amps. 0.033 amps is actually 33 milliamps. And our target was 15 to 20. So what we've worked out is that this resistor is a little bit too small, actually. It's not got quite enough resistance for the circuit, and it's likely to lead to overheating in the LED. It's not a problem for short-term usage, but over the long term, if you were to have this in a product, you'd expect that LED to wear out a bit faster than it should do. So what we conclude from this is either that our battery voltage is too big, which it is slightly, or that our resistor is too small, which it also is slightly. We can work out the power use for the resistor and make sure that that's in spec as well. So we have our formula, P equals I times V. We can apply that to the resistor. We know that the current now is 0.033, and we know that the voltage across the resistor is 7.65 volts. So multiplying these two numbers together is going to give you the amount of power that the resistor is eating for you. 0.33 times 7.65. 0.25 watts. The unit of power is watts. And it turns out that is actually exactly what we want. These resistors are rated for 1/4 of a watt, 0.25 watts. So we're using the maximum amount of power that this resistor can handle. In reality, over the long term, that's probably not good for the resistor either. So you'd increase the power rating of the LED, or increase its resistance, or reduce the voltage of the battery in order to make that power usage a little bit less. In order to get the power usage for the LED, we're going to do the same thing, but with the LED voltage instead. So instead of 7.65 volts, we're going to use 2 volts, which is how much the power drops across the LED. Times 0.033 gives us 0.066. 0.066 watts. It's using 66 milliwatts, which is a pretty reasonable amount for an LED. And that concludes it. Thanks very much.